Welcome back, calculus. Even though I can't be with you today, I wanted to make sure you could get these related rate problems. We were finishing up with this problem with the rocket ship taking off and finding the rate of change of the elevation. We had almost finished it. I had this part here where we took the derivative and got cosine squared over 2400 dy dt, and we're trying to solve for d theta dt, the rate of change of this angle of inclination. And so we had to find this theta, and I think that's where we kind of left it. So we have a triangle here, and the triangle has an opposite side of 700 and adjacent side of 2400, so we can use tangent to find theta. And specifically, we're going to use inverse tangent or arctangent. And if you put this in your calculator, you take arctangent of 700 over 2400, that's going to give you theta. Make sure that your calculator is in radians as well, so that's important. And if your calculator is in radians and you type this in, then it should come out to 0.28374 and so on. I would leave that in there and then just take cosine of that. So do cosine and then the previous answer. And then you want to also square that. And when you take cosine squared of this, 0.28379, and then divided by 2400, multiplied by 600, because that's what dy dt is. Your final answer should come out to 0.2304 something, which you need to make into a fraction. And if you make that into a fraction, it's going to come out to 144 over 625, and that's going to be radians per second. So that finishes that problem. All right, the first three problems are pretty hard. The next set of problems should be fine easier. So I'm going to go on to number 7. And with these problems, like I said, they're a little bit easier because they're just going to be using familiar formulas that you already know. So this one, if you read it, it says water leaking onto a floor forms a circular pool. The radius of the pool increases at a rate of 5 centimeters per minute. How fast is the area of the pool increasing? So this has to do with a circle, and like with all these related rate problems, you want to draw a picture. And so the picture that you might draw is a circle with a radius, and that's r. And I'm going to bring that out here, and the r is going to change over time because the circle is getting bigger over time. So the radius is going to go out, and therefore the circle is going to go out, and the area, we're also talking about area, that's going to change, and that means that we're going to have a rate of change for the area. And so now what? Now we want to be able to relate these, radius and area. What's the formula for the area of a circle that uses the radius? Well, that's area is equal to pi r squared. And then we're going to, now that we have this formula, we're going to differentiate it with respect to time. So that's going to give us dA dt is equal to 2 pi r. You might recognize that 2 pi r. That's the circumference of a circle. So it's kind of interesting that the derivative of the area, gives you the circumference of a circle. And of course we need a dr dt here. And now what do we want to solve for? We want to solve for how fast is the area changing. So that's what we want to solve for. We know that at a particular time the radius is going to be 14. We know that the rate of change for the radius is 5. It's going to be positive because the pool is increasing. So that's going to be a positive 5. And now we can start to plug in. So we get dA dt is equal to 2 times pi times r. Well, the r at this specific time is going to be 5. And dr dt is going to be 14. And we are going to keep it in terms of pi here. So 2 times 5 is 10 times 14 is 140 pi. And we can write dA dt. So 140 pi, what are the units? This is in centimeters squared because we're talking about area over time. So remember, if we go back to our differential here, the derivative, we got the area with respect to time. So area is measured in centimeters squared, and time is measured in seconds for this one. Oh, nope, sorry, minutes. Minutes, actually. So it's centimeters squared per minute. And so that's going to be our final answer. Next problem I want to go over is number 9. And here it says a slime cube grows so that the length of its sides are increasing at a rate of 2 meters per minute. How fast is the volume of the cube increasing when the sides are 3 meters each? So we're going to draw our slime cube and make it look something like this. And this slime cube is getting bigger and bigger. And so that means that the sides here are going to get bigger as well. So each of the sides for a cube is going to be the same. And so we might have a side length at a particular time. And we're going to have a rate for the side. And this problem is also talking about volume. So we'll have maybe a volume and a rate of volume. So I just like listing out all the variables and then seeing how they relate and how can we relate sides and volume. Those are the two things that this is talking about, the side length and the volume. Well, for a cube, it's just s cubed. So that formula is going to tie all these variables together. And now let's take the derivative on both sides with respect to time. So we're going to have dv dt. And that's going to equal, we got to use the power rule over here, 3s squared. And chain rule ds dt. And what do we want to find? We want to find how fast the volume is. So this is what we want to find. And we know two things. We know that it's increasing at a rate of 2. What's increasing? The side length. So it's getting bigger, so that's going to be 2. And the side length at a particular time is 3 meters. So we can plug that in, so we can solve for this, dv dt. So that's going to be 3 times s squared. That's going to be 3 squared. So we just plug that into there. And then ds dt is going to be 2. And we're going to multiply that out. So 3 squared is 9. 9 times 3 is 27. Times 2 is going to be 54. And the units, well, it's easiest if you go back to here. Let's talk about volume. Since these units were in meters, the volume is going to be in meters cubed. And it's volume over time. And the time unit we're talking about here is minutes. So this must be meters cubed per minute. So 54 cubic meters per minute. That's it for that one. So like I said, these ones I think are a lot easier. It's not till we get to the last one that it's a little bit trickier. Okay, number 11. All right, here's number 11. We have a spherical snowball, and it's melting at a rate of 32 pi over 3 cubic inches per second. So, got to make sure when it gives you a rate, what is that rate talking about? And it says, at what rate is the radius of the snowball changing when the radius is 9 inches? So we're going to have ourselves a ball or a sphere. So I'll draw a picture to represent it. And this one is melting, so I'm going to draw my arrows going in to kind of show to myself that it's getting smaller. And so the radius is going to get smaller. And so we're going to have some things here. We're going to have a radius. We're going to have a rate of change for that radius. And it also, what else is it talking about besides the radius? Well, what is this? If you look at these units, these are cubic inches, so it must be talking about volume as well, and a rate of volume. What do we want to find? We want to find out what rate is the radius changing. So here, that's the unknown that we want to get, is dr dt. And this is going to be 32 pi over 3 is going to be the dv dt. It's melting, so that means it's going to get smaller. So we're going to have a negative. And the radius at a particular moment is going to be 9. So how do we connect volume with the radius? Well, the formula for volume of a sphere is 4/3 pi r cubed. And now we can take the derivative. This is volume of a sphere. You get all these formulas on that formula sheet, or you can just look them up. When you take your test or whatever, a quiz, of course you can have these on a note card. And we're going to take the derivative. So we got dv dt. Do the power rule. So this 3 is going to come out. I'll just write it here. We're going to have 3 times 4/3 times pi. Drop it down to power dr dt. this 3 and this 3 would cancel. So really we have 4 pi r squared, which if you know what the surface area is for a sphere, that's exactly what the formula is for the surface area. So this is the volume, and this 4 pi r squared, that's the surface area. So again, it's kind of interesting how these are related to each other when you take the derivative. And we want to get dr dt by itself. So if I simplify this a little bit, we want to solve for dr dt. And let me put that on the left side here. And so that means we're going to have to divide by 4, divide by pi, divide by r squared. So we're going to have 1 over 4 pi r squared because we're dividing by all those. And then we've got the dv dt. Plug in what we know. So we know what r is. R is 9 squared. And dv dt is 32 pi. And it's negative over 3. So we can simplify this. 32 divided by 4 is 8. And then we're going to have our, what do we have on top here? Negative 8 times pi. So negative 8 pi. On the bottom, 9 times 9 times 3. That's 81 times 3. 81 times 3 is 243. So we got negative 8 pi. Oops, sorry, the pi is also canceled out. I forgot about that. So it's just negative 8 over 243. So pi's cancel out as well. And so we got negative 8 over 243. And that would be inches, because we're talking about radius over time. So inches per second. I think it's seconds? Yes, seconds. So there is our final answer. Negative 8 over 243 inches per second. So this one's a little bit different because now you're solving for a dr dt. So you got to flip the formula around a little bit. All right, now time for our last problem. And I was going to do 13 because I usually do the odds, but I'm going to do 14 because here the 10 and the 10, the numbers are the same. So it's not going to be as obvious when I set it up, how I'm setting it up. So I wanted you to do 14 here so that you can see how the setup is using different numbers. I think it'll make it a little bit easier to see. So here we're talking about a conical paper cup, and it's 10 centimeters tall with a radius of 20, and the bottom of the cup is punctured, so the water level goes down at a rate of 2 centimeters per second. At what rate is the volume of the water in the cup changing when the water level is 8 centimeters? So we're going to have our cup here. It's a cone. Draw a picture. We've got a radius. This radius is not changing. It's 10. It's 20 in this one. So this is 20. The height of this cone is 10. And this cone is filled with water. So there's the water level. And the water level also has a height. And the water level also has a radius. And the water is going to be, leaking out. So this is going to be going down. So the water is going to be coming out of here. The volume of this water is going to become less. And that means that the height of the water is going to become less. And the radius is also going to become less. Now, when you look at the formula for volume of a cone, it is 1/3 pi r squared h. And so now it looks like you got 1, 2, 3 variables. So that's what makes this a little bit more tricky, because it looks like you got 3 variables, but in actuality, we don't really care about the radius, because all it's talking about is a height, and that's the change in the height, and that's the height at a particular time, and it's talking about the volume, which is how much water is in it, or how much water is leaving. So we don't really care about the radius here. So what we can do with this is, again, use similar triangles. So similar triangles are used in a lot of different mathematical problems. So if I just focus on this, the cone, we're told, has a height of 10. If if I go from the top to the bottom, and it's got a radius of 20. But we've got this little triangle inside. This is the water level. And we've got the height of the water level. From here to here is the height of the water. And we got the radius of the water level, or the radius of the water that's inside. So we've actually, again, kind of like the shadow problem, we've got similar triangles here. So I could set up a proportion. Now, in this formula, I don't need to know anything about the radius. So I'd like to get rid of the radius. And so to do that, I want to solve for the radius. So I'm going to set up a proportion. I've got this side of the triangle over h is equal to, well, this r here corresponds to this length of the triangle at the top, which is 20. And then this is the height of the little triangle, and the height of the big triangle is 10. So now I have a proportion. I can simplify the right side, and it just comes out to 2. And if I get the r by itself, I would have r is equal to 2 times h. That means that anywhere I have an r, I can substitute 2h. So I can go back to this formula and plug in 2h everywhere I have an r. But I got to remember that r here is being squared. So that means that this whole 2h has to be squared as well. So that's, again, another tricky part is some people, you might forget to square the 2. But 2h is equal to r, and we're going to square that, and we're going to multiply by h. So if I simplify this a little bit, I have pi, and then 2h squared is going to be 4h squared times another h. Move this 4 to the front, that's going to be 4/3 pi h cubed. Okay? And I still haven't taken the derivative yet. I'm just simplifying this formula down so that now I have it in two variables, v and h, because those are the only things I care about, is the volume and the rate for the volume, and the height and the rate for the height. So now I'm going to do some calculus and take the derivative. So we take dv dt, and over here we have to use the power rule. So the 3 is going to come out, and it's going to cancel with that 3. So it's going to leave me with 4 pi. H drops down a power, so now it's 2 dh dt. And now we're all set. Now we just plug in everything that we're given. Well, what we were given up here. So the 10 and the 20, we already used those. That's to set up the proportion. It says it's going down at a rate of 2 centimeters per second. So that is our dh dt is going to be -2 because it's decreasing. And h at that particular time is 8. Well, that's exactly what we need. So we have all the things we need to plug in here to find out what dv dt is. So dv dt is going to be 4 times pi h squared. Well, h, again, the height of the water level at that particular time is 8. We're going to square that. The rate that the height is changing is -2. So I'm going to multiply that by -2. And simplify this out. So 8 squared is 64. Multiplied by another 8 is going to be 512, and it's going to be negative. And I'm going to keep the pi with it. So 4 times 8 times 8 times -2 is going to be -512. Still got the pi. The units, well, what are we talking about? Volume and time. So volume is cubic centimeters here. Time is in seconds. So there is the answer for that one. And that's all the different types of problems. So once you get to 15 through 20, they are similar to the ones before. So gone through every single type of related rate problem in this packet. So with that information, you should be able to finish it and get it turned in. Let me know if you have any questions, and we'll see you later. Bye!